Quiet. Alright, let's do a problem. A spherical shell of radius 6 cm carries a uniform surface charge density sigma equal to 9 nanocoulomb per meter squared. What is the total charge on the shell? Find the electric field at R equal to 2 cm, at R equal to 5.9 cm, at R equal to 6.1 centimeter, and at R equal to 10 centimeter. Well, all we need to do is use the formulae we derived. The radius of the shell is 6 centimeter, 0.06 meter. The surface charge density is 9 nanocoulomb per meter squared. Now, area of the shell, you know, is 4 pi r squared, where r is the radius of the shell. And therefore, can you calculate the total amount of charge carried by the shell? If the radius of the shell we know is 0.06 meter, the area of the shell, the spherical area, will be 4 pi r squared. And that will be, if you know your R, we can calculate the area. The total charge on the shell will be the area multiplied by the surface charge density. Is that right? Sigma stands for charge per unit area. Multiply that with the area, you will get the total charge on the shell. So the total charge on the shell is 4 pi r squared times sigma. You know the radius, you know the value of sigma. Using that, the value of Q equal to 4.07 times 10 to the negative 10 coulombs. So now you know the amount of charge on the spherical shell. And what is the equation for the electric field at a point outside the outside the charged shell? It will be KQ over R squared. So all you need is the value of Q and the value of R. Alright, let's start with the first A. Find the electric field at, what's the first point we need to find? At R equal to 2 centimeter. That's right. Find the electric field at R equal to 2 centimeter. Tell me, where is this point? The radius of the shell is 6 centimeter. Therefore, a point R equal to 2 centimeter is inside the shell. What is the electric field inside the shell? Is 0. So, what is the electric field at a distance R equal to 2 from the center of the shell? Field at any point inside the shell is 0. Therefore, the electric field at that point is 0. How about C? What is the electric field at R equal to 5.9 centimeter? Because the radius is 6 centimeter, R equal to 5.9 centimeter is also inside that shell. And again, the electric field is 0. So, we've done A, we found the amount of charge on the shell. In B and C, both these points are inside the shell. The electric field inside the shell is 0. How about D? Electric field at R equal to 6.1 centimeter. It is outside the shell. There is a value for field there. Field at any point outside the shell will be E equal to KQ over R squared. We just calculated Q, we know it. R is 6.1 centimeter, 0.061 meter. So R equal to 6.1 centimeter, which is 0.061 meter. KQ, Q we calculated as 4.07 times 10 to the negative 10 coulombs. And R is 0.061 meter. The electric field is 984.4 Newton per coulomb. And how about the electric field at R equal to 10 centimeter? Well, that again is an outside point. What all we need to do is replace your R by 0.1. So at R equal to 10 centimeter, electric field is KQ over R squared, where R is 0.1 meter, that is 366.3 Newton per coulomb. Alright, let's look at another problem. A spherical shell of radius R1 carries a total charge Q1 that is uniformly distributed on its surface. A second larger spherical shell of radius R2 that is concentric with the first. So you got a first spherical shell of radius R1 and a second spherical shell, a bigger one, which is concentric, means both have the same center. So the first shell is inside the second shell. Now that is distributed uniformly over its surface. Use Gauss's law to find the electric field in the regions where R is less than R1. What does that mean? R is less than R1. R1 is the radius of the first shell. R is less than R1 is inside the first shell. Now R1 less than R less than R2. You see, you have an inner shell and an outer shell. So R1 less than R less than R2 is any point in between the inner shell and the outer shell. And then find the electric field at points corresponding to R greater than R2, that is outside of both shells. What should be the ratio of the charges Q1 by Q2 and their relative signs for the electric field to be 0 for R greater than R2? If you want the electric field to be 0 outside the system, what must be the ratio of the two charges and what must be their signs? And finally, sketch the electric field lines for the situation in B when Q1 is positive. Well, you know how important it is to get a mental picture of a problem. Always read a problem a couple of times and form a mental picture. Alright, now here I have the inner shell and the outer shell. The radius of the inner shell is R1 and the radius, and it carries an amount of charge Q1 that is uniformly distributed on it. The radius of the outer shell is R2. Well, I think my line went a little overshot. It must stop here. So the radius of the outer shell is R2 and it carries an amount of charge Q2. Okay, what is the first thing that we need to find? Use Gauss's law to find the electric field at a point such that R is less than R1. You see, the small r is the distance of the point you want to find the electric field from the center. If R is less than R1, it means it is a point inside the inner shell. Now, what is the electric field inside that inner shell? The field at any point inside the shell is 0. Therefore, the electric field at a point R less than R1 is 0. The electric field at a point inside that inner shell is 0. Now we want to find the electric field at any point between the inner shell and the outer shell, somewhere here. R1 less than R less than R2. Now, how do you find the electric field there? Well, if you take a point here, that point is inside the outer shell. That means the electric field due to the charge on the outer shell will be 0 there, and it is outside the inner shell. I hope you follow my argument. If you take a point here, it will be inside the outer shell and outside the inner shell. That means the field at that point will be purely due to the charge on the inner shell. Alright, let's write that down. For a point in between the inner and outer shell, these points are inside the bigger shell and outside the small shell. Now, the bigger shell will not contribute to the electric field because the electric field inside the shell is 0. But the inner shell will contribute. The field at points in this region, in the region between the two shells, is purely due to the charge carried by the inner shell, which is Q1, the charge on the inner shell. And what is the mathematical expression for that field? The field at any point in between the shell will be purely due to this Q1, which will be KQ1 over R squared. That will be E equal to KQ1 over R squared. That is the expression for electric field at any point in between the two shells. Alright, how about the next one? For R greater than R2. See, R greater than R2 means a point outside of both the shells. And the field outside of both the shells will be due to the charge on the outer shell as well as the charge on the inner shell. It will be due to Q1 plus Q2. So that will be E equal to K. The total charge will be Q1 plus Q2 over R squared. At any point outside of the two shells, the electric field will be K times the total charge on the two shells divided by R squared. And B, for the electric field to be 0. Now we have been told to find the ratio of the two charges which will result in the electric field outside to be 0. Now when will this become 0? This is a rational expression. This is the electric field outside the two shells. And in B part, we have been told to find the ratio of Q1 to Q2 that will result in the field at any point outside to be 0. Now tell me, when will this quantity become 0? This rational expression becomes 0 only when Q1 plus Q2 becomes 0. If Q1 plus Q2 equal to 0, it means Q1 equal to negative of Q2. You see, this is the only way the electric field at any point outside the system can become 0. So if the electric field outside is 0, it means Q2 equal to Q1 or Q1, well, Q2 equal to negative Q1 or Q1 equal to negative Q2. That means Q1 divided by Q2 will be negative 1. So, if the field outside the system is 0, it means if the charge carried by the inner shell is positive, then the charge carried by the outer shell must be